In this 11th podcast, we're going to continue with bonding between atoms. In the last podcast, number 10, we looked at ionic bonding, where atoms give or receive electrons, resulting in the atoms becoming ions and becoming charged. And when they gain these opposite charges, they stick together to produce ionic solids like sodium chloride. Now these bonds tend to be very strong, and as a result ionic compounds are often solids. So the second bonding technique we're looking at is covalent bonding. And covalent bonding is slightly different. The goal is the same. The atoms desire full outer or valence orbitals. In ionic bonding, they give or receive electrons to achieve this, but in covalent bonding, they tend to share electrons to achieve this. So the electrons are not given outright, forming individual ions. The electrons are shared, giving the atoms the sensation, if you like, that they have full outer orbitals. The name covalent indicates that there's a necessity for two valences, or the outer orbitals of two atoms needed to achieve this bond. Now let's take a look at an example. So water is a very common substance, very well-known substance, and most people know that the chemical formula for water is H2O. H2O, I'll just write that down up here. H2O. Now that's telling us that water has two hydrogens and one oxygen. Two hydrogens and one oxygen. And the bond holding these three atoms together is covalent bonding. Actually, two covalent bonds. Because we have an oxygen and that is stuck to two hydrogens. So let's see how that looks. So there's my oxygen and there's my two hydrogens. And these are the valence orbitals, the outer orbitals or valence orbitals here. I haven't drawn the particles in the nucleus because I'm not interested. I haven't actually drawn, in terms of oxygen, the first orbital, which contains two electrons, because that is not involved in the bonding. It's just the valence orbital, the outer orbital, which is involved in the bonding. So this hydrogen bonds with the oxygen and it shares its electron. Let's rotate that round there and slide that in place there. It shares its electron with the oxygen. This hydrogen also does a similar thing, so I'm going to rotate that around so we can slide that into place like that. So you can see now that the electron orbitals, the valence orbitals, are overlapping. And if you look at now the oxygen's valence orbital, if we count through, we now have 8 electrons, which is a full valence orbital for oxygen, because its outermost orbital contains or can contain 8 electrons. The hydrogen only has one orbital. Initially it had one electron, but now it's sharing with oxygen, so each hydrogen appears to have 2 electrons in its valence orbital. So full orbitals, full valence orbitals for all. So this is a molecule of water. Molecule, we use that term for a covalently bonded compound like this. Molecule of water. And this molecule of water will stick to other molecules of water for various reasons, and the bond between different molecules of water, between this molecule and another, is not so strong. As a result, this compound at room temperature is not a solid, it's a liquid. As you know, water is liquid at room temperature. And many other covalent compounds, such as carbon dioxide, carbon monoxide, are also not strongly bonded. Each molecule is not strongly bonded to the next. In fact, with carbon dioxide, the bonds between the molecules are so weak that it's a gas at room temperature. Let's take a look at some more. So here's oxygen. Now oxygen, pure oxygen gas in the air we breathe is O2. Oxygen, pure oxygen is never found by itself. It always teams up with another oxygen atom to form what we might call a diatomic molecule. So it has two atoms of oxygen. Now we can see from these diagrams here, in this diagram, why that happens. Now oxygen is in group 6 over here. So we know that being in group 6, it has two spaces in its valence orbital. Two spaces in its valence orbital. And there we can see 6 and 6. Now if two oxygens get together, like this, I'm just going to rearrange these two a little. Just move that around there. Move that around a little further. We can see if they get together and their valence orbitals overlap, they can achieve full orbitals by sharing. Now in this case they're sharing 2 electrons with each other. This atom is sharing 2 electrons with this and vice versa. But we can count through 8 in this valence orbital and 8 in this valence orbital. Now because they're sharing 2 electrons each, we would call this a double bond. So here we have bond 1 down here. Bond 1. These electrons here overlapping, forming bond 1, and this could be bond 2 up here. These 2 electrons here forming bond 2. Now let's consider hydrogen. Now hydrogen does the same thing as oxygen. You don't find hydrogen gas as individual atoms. They form molecules of 2 hydrogen atoms. So pause the video and try this one yourself. Write down in the same way as I've done little pictures for hydrogen and overlap them and see what you get. Okay, so check your diagram with this. So there's my 2 hydrogens. In the valence orbital we have 1 electron and that's it. A full valence orbital for hydrogen would only be 2 electrons. Easily achieved by overlapping those valence orbitals. Slide this one over and there we are. So that's 1 bond in this case. This is only 1 bond. But you can see that the valence orbitals for both atoms appear to have 2 electrons and they're both quite happy. So that's hydrogen gas. Now how about carbon dioxide? Carbon dioxide, pretty well known gas, CO2, 1 carbon, 2 oxygens. So here they are, 1 carbon. Carbon is in group 4. Let's just check that out. Carbon is here in group 4. So element number 6, 2 electrons in the first orbital, 4 electrons in its valence orbital. So there we are, 4 electrons in the valence orbital there. And we have our 2 oxygens down there. Carbon dioxide. Now what's going to happen here? Let's have a look. So this oxygen needs 2 more. This oxygen needs 2 more, and carbon needs 4 more. So again, these orbitals, these valence orbitals, are going to overlap. Let's twist that around a bit and see if we can achieve that. There. And here, we're going to have to twist that around a bit more. A little more. Something like that. So now we can see this oxygen has 8, this oxygen has 8, and carbon, due to the sharing, also has 8. And here we can see we have a double bond between the carbon and the oxygen, a double bond between the carbon and the oxygen. Bond 1 and bond 2 on both sides. This would also be bond 1 here, and this would also be bond 2 over there. And the final example, methane, flammable gas produced when organic materials decompose, and that is CH4, 1 carbon and 4 hydrogens, and we can see them all arranged nicely here. Should be clear that each hydrogen requires an extra electron to share with, and the carbon needs an extra 4 because its valence orbital for fullness requires 8. So I'm just going to take these in. Going to need to rotate this one round before I take it in. There we go. Also, rotate this one there and rotate this one round. So now we can see everyone's happy. Each hydrogen has 2 and the carbon has 8. So this methane molecule here is forming bonds between the carbon and the hydrogen, and they're single bonds. 1 pair of electrons is a single bond. Compare that again with carbon dioxide, 2 pairs of electrons between each atom, 2 pairs of electrons, a double bond. So that's the basics of covalent bonding.